So thank you, Stefan, for the invitation, and thank you all of you to be there. So it's my pleasure to present you Shor algorithm. And so during this talk, I will show you, in fact, some other kind of algorithm, and I think I will be a little bit more concrete than the talk before, but I think it was a very good introduction to the area. During the first part, I will show you some very basic circuits in order to understand maybe more how it works, and I will also show you some example. I think a lot of example to know how to work with such algorithm. Then I will move on one of the first algorithm, which is Dutch-Josa algorithm, and I will show you how it works and what kind you can expect from such quantum algorithm. Then I will describe you a Shor algorithm, and at the end I will also show you how you can implement the discrete Fourier transform using quantum circuits. So let me begin with by just recall you how one of the most important quantum gates, that is Hadamard gate. So as Giulio presented, you just apply the Hadamard transform on each qubit state. So for instance, if you begin with the ket 0, you get ket 0 plus ket 1. And if you input is ket 1, so you get ket 0 minus ket 1. And you can also extend this by linearity, and just before h is a linear operator, and so you can just compute alpha time h of ket 0 plus beta time h of ket 1. And so you will get some formula, and if you do the math, so it's not very complicated to see how any other quantum state can be mapped to this basis. So the other kind of presentation is using some linear map. And since this is one qubit gate, so you can describe it using 2x2 matrix. And the matrix will be the following. So if you apply ket 0 from this matrix, so it's exactly the same that if you compute with the matrix MH times the vector 1, 0. And so you will get, in fact, the first column of the basis, and this is exactly what you expect. So similarly for the ket 1, so if you apply to this matrix, so the vector 0, 1, so you will get the second column of the matrix. And more generally, if you apply this to any psi, so I show you some examples, so I hope that you will be able to do this. So either you can use the formulas that I described in the second point, or you can also compute it using the matrix time vector product, and you will see exactly the same result. Okay? So now that we have such a gate, so we can have some circuits, and so this is the way that we describe circuits. So we begin, for example, with ket 0, you apply some gate. So the X gate is in fact the gate that switch ket 0 to ket 1 and ket 1 to ket 0. And just after you measure the value. And so if you begin with ket 0, so after X you will get ket 1. And if you measure this quantum state, you will get 1 with probability 1. Okay, this is the same also if you begin with ket 1, so you will get 0 at the end. And so this is very easy to go through all the computation by looking step by step what will be the state. Okay, so this is what I present you just after the X state. So if I apply this to psi, I will get beta time ket 0 plus alpha time ket 1. And so if I measure this quantum state, I will get 0 with probability norm of beta square and 1 with probability alpha square. Okay? So I can do the same with the Hadamard transform. And so you will see that we will get, if we begin with ket 0 or ket 1, 1 and 0 with probability 1/2 in both cases. Okay, so now that we have seen 1 qubit gate, let's move on to 2 qubit gates with some example, and maybe you will more understand the tensor product. So now I have a 2 qubit quantum state, psi. So I describe it using the basis 0, 0, 0, 1, 1, 0, and 1, 1. And alpha, beta, gamma, and delta are complex number, so that some normalization relation holds. And when I compute the tensor product of these two vectors, two-dimensional vector, so I will get, in fact, A times the second vector, so it's the two first coordinates, so you have AC and AD, and then, so the two bottom coordinates are in fact B times the vector CD, so this is BC and BD. Okay, so it's not difficult to see that, in fact, this tensor product is not commutative. If I compute this in two different, I will get, in fact, maybe two different results. And for instance, if I begin with a ket0 times ket0, so it's exactly 1, 0, tensor 1, 0, and so you will get 1, 0, 0, 0, and it's exactly ket0, 0. Okay? So I can do this with all the different basis vectors, and I will get, in fact, all the four-dimensional basis. And so any 2 qubits state can be described by linearity using alpha, beta, gamma, and delta using a four-dimensional vector. So I can do some computation with these qubits. For instance, I can add two different 1 qubits. So if I have a psi and phi and psi, so I can just add them using some basis. So I just add each coordinate. So it's very easy. I can do also the same for 2 qubits using this four-dimensional basis, and it's exactly the same. And I can do also some multiplication, so what is called tensor product. And so maybe it's more easier to work with multiplication notation using the ket notation. And you will see that it's exactly like if you develop. For instance, if I have 1 plus 3i times ket0 plus 2i times ket1 times 3 times ket0 plus 1 minus 1 take ket1. So I just will develop 0 on both vector. So for the 0, 0, I will get 1 plus 3i times 3. And for 1, 0, it's in fact the first coordinate, 1 plus 3i, times 1 minus I. Okay, so if I do the math for this complex multiplication, I will get 4 plus 2i. Okay, so it's not very complicated to see. I have not described in all the... So you have a question? Yeah, I haven't, so the question is, I haven't normalized this vector. So it's basically because we can always do, it's not complicated to do the operation, and it's not gain you many more information, in fact. And also, it makes the formula easier to understand. Okay? There is no other question? So, as Julio mentioned, so the CNOT gate is one of the most 2 qubit gate important, and it's called a control gate. And so let me explain you maybe how it works. So it will map, in fact, the state 0, 0 to 0, 0, 0, 1 to 0, 1, 1, 0 to 1, 1, and 1, 1 to 1, 0. Okay? So I can, in fact, describe the matrix multiplication for such operation. So now, since it's a 2 qubit gate, so it's a 4 by 4 matrix. And in fact, nothing happened for the first qubit. So that's why on the right-left corner, you have, in fact, the identity. So the identity means that for the first qubit, so you don't do anything. It's the identity. Okay, but for the second qubit, you have something, so it's more what is called an inversion, and it means that if the first qubit is 1, so you invert the value. Okay, so this is why it's called a control gate, is that if the first qubit is a 1, so you apply, in fact, the operation on the second qubit. Okay, so if it's a 1, so now if the second qubit is 0, so the output will be 1. Okay, sorry. So that means that, so now you have a 1 for the first qubit, the second qubit is a 0, and so if you have here a 1, and the second qubit is 0, you have 1 XOR 0, and it will be 1. So that one here, for the second qubit, you have a 1. Okay? And it's exactly the same for this state. So since you have a 1 for the first qubit, for the second qubit here, so you have 1 XOR 1, and it will be 0. Okay? That's why, because here you have a 0. Okay? So it's what is called control NOT. Okay. So what made this two-qubit state very interesting is that for, in fact, generating more general circuits, and as Giulio mentioned, in fact, every quantum circuit can be described by some unitary matrix, and so the matrix has to be invertible. So it is a case because here you have A star A equals the identity. Okay, but more generally, every n-qubit circuit can be, quantum circuit can be described using only C0 gate and 1 qubit gates. Okay, so this is a very important theorem. And as Giulio mentioned, there is also sort of a Kita-F result that explains you that any 1 qubit gate can be, in fact, well approximated using the so the two 1 qubit gate, H and the T gate, and also using the 2 qubit gate, the C0. Okay, so this is an approximation theorem, and also I will not go through this result. And also, as Giulio mentioned, the Toffoli gate is what is called a universal gate, because every quantum circuit can be describing only using Toffoli gate. So you can, in fact, see that you can implement the NAND gate. However, if you are quantum programming, in fact, you try to avoid Toffoli gate. Toffoli gate is good in a theoretical point of view. However, if you want to implement them, so it requires a lot of C0 and other gate, and so at the end, the circuit will be not very efficient. Okay, so that's why when you see the estimation for some circuit, usually people give you the number of C0 and Hadamard gate, and also the number of Toffoli gate, and they try to reduce the number of Toffoli gate as much as they can. So for the partial measurement, also I will, so since it's very useful for Shor, I will show you some number in order to get more familiar with such operation. So if, yeah.
Yes, why do we have this C0 gates here? I mean, if you just don't want to invert Can I ask you, why do we have these C0 gates? If we just don't want to invert some bit, then we simply can abandon applying this gate. Why do we need this control bit here?
So this gate is one that can allows you to mix, in fact, two different qubits in some way. Otherwise, if you have only, so I don't know exactly, but it's something that I can imagine. So it's to have some mix between qubits.
Oh, thank you.
Okay, so if you have this general 2 qubit, so what happens if you measure 1 for the first qubit, for instance? What will be the second qubit? So in fact, let me show you with some examples. So I have this state. So now I assume that the second qubit, I measure the second qubit and it is 1. So I assume that this comes from this state. And so if I measure the first qubit and if it's a 1, so I am sure that the second qubit will be a 1. Okay? And now, if I observe, in fact, 0 for the first qubit, so it can be on this state of this one. And one of the most easiest way to work and to compute with this is that in some way to factorize with the first qubit. So in fact, I can factor this 0 into the 2 different states, and I will get, in fact, this new state. And right after normalization, if I observe 0, so for the first qubit, so the second qubit will be that one. Okay, so you just have to factorize with the 0, and you will get the result. So more generally is a formula that Giulio presented before. And so I just give you some exercise if you want. And I have a 3 qubit state. And now if I measure 0, 0 for the first 2 qubits, so now you will see that you have only these 2 states that begin with 0, 0. And in fact, you just have to normalize these 2 qubit state. Okay? So now let's move on. Is there any questions so far? No, it's okay. Okay. So let's move on to some more precise quantum circuits. And let me just explain you what is called an oracle gate. That is, in fact, some gate that implement any kind of function. However, as Giulio mentioned, we cannot have such a gate because it's not reversible. And so we have to do something, in fact, to transform the function into a bijection. And so if you have followed some cryptographic course so far, so you know how to transform any function into a permutation. So even if you do some symmetric crypto, so it's usually we use what is called a Festel scheme. So it's the purpose of Festel scheme, in fact, to transform any random function into a random permutation. And the idea is just, in fact, to copy the first qubit, and in fact, to add the result to the second. Okay? And so it's not difficult to see that, in fact, it is a bijection, and maybe you did it before. And so the idea is just, in fact, to see that f is on inverse. And in fact, to show this is that you just see that if you apply f twice, in fact, you go back to the previous result. Okay? And so this is also the reason why, during the death scheme, you can also implement it very easily. If you have one implementation, you have also the implementation of the inverse. Okay, but for a more general function that take a k bit to 1 bit, so the idea is that you have to copy all the bits for the x, and only apply this for the second to the y and to the last qubit. So the problems that Dutch and Josa problem try to solve is the following. So assume that you have some bit functions that operate on bits. So f transform one bit to another bit. And so you can have, in fact, 4 different kinds of such functions. And 2 of them are constant, and the 2 others are what we call balanced. That means that they take exactly the same number of 0 and 1. And so, for instance, you can, for four such functions. So the first two are in fact constant. So you can see that the output is 0 or 1. And for the F2 and F3, you see that they are what we call balanced because you have 1 time 0 and 1 time 1. Okay? And so the goal is to decide if F is a constant or a balanced function. Okay, so classically you can do this by asking what is the result of F0 and what is the result of F1. And so you compare. If they are the same, so you answer that they are constant. If they are different, you say that they are balanced. Okay? But I will show you that you can do this using only one quantum query to the quantum circuit oracle. Okay, so maybe it's not very impressive, but in fact, we can also generalize this to any n-bit function to a one-bit function. Now, it's not the case that all such functions are either balanced or constant, but if you have the premise that they are in one of these two categories, in fact, you can decide, so the problem is to decide on which category, balanced or constant, the function is. Okay, so classically you can do this using 2 to the n-1 plus 1 query, because if you begin with, so if the function is balanced and you begin with only, for instance, 0 output, so maybe you only ask the function for the value that the function is giving to 0, and you have to wait up to the query, which is 2 to the n-1 plus 1. Okay?
But if you put randomize.
Sorry? If you can, yeah. Yeah, I agree with you. So the question is that if I can randomize so the evaluation of the function, so I can do this more efficiently than the classical functions that the classical algorithms that I described. Okay. But in fact, yeah, I think you can do more than one query. So, what you can do, in fact, you can do this using only one query. And so you can see that sometimes you can have an exponential gap between what you can do classically and what you can do quantumly. However, it's not the same for every problem. You cannot have such an exponential improvement. And so I will show you one other example, such as the factorization problem. So how works Dutch and Josa algorithm? So I think it's very useful because it's not completely trivial to understand. And it will show you how we can manage to use Hadamard gate and the Oracle gate at the end. Okay, so in fact the circuit is not too complicated. In fact, for the case of n is equal to 1. And I will let you to generalize this for n equal 2. And for n equal 3, the equation is also more harder to follow. But you can do this formally. So for the first, so you see that the input of this circuit is ket 0 for the first qubit and ket 1 for the second qubit. You can also begin with ket 0 if you want. You just have to add X gate. Sorry. If you want to transform this one from a 0, you just have to input it the X gate, and the goal of the X gate is to exchange 0 to 1. Okay, so if you want to begin with 0 for the circuit, it's also possible. And so we apply, in fact, 2 Hadamard gates for each line. Afterward, we apply the Oracle function, which is described here. Okay, so this is the F function, so we don't know exactly what is F, and we want to discover if it is constant or balanced. And at the end, we also apply some Hadamard gate right before we measure this qubit. Okay? So usually we split, in fact, the circuit into different steps. And we try to look what is the quantum state across the whole computation. Okay, so we begin with the state 0, 1. And right after the Hadamard gate, so we will get, in fact, psi 1. So we apply, in fact, the Hadamard gate on the 0, ket 0. And so we will get this qubit. So I have not normalized the qubit, but you can do this. And for the second qubit, you will get ket 1. Okay, so this is the state here. You can develop if you want. So you will get 0, 1 plus 1, 1. And after the second Hadamard gate here, in fact, we have a 1. So if I apply h to 1, I will get 0 minus 1. Okay, so the state C2 is in fact 0, 0 minus 0, 1 plus 1, 0 minus 1, 1. Okay? So now I will apply the oracle function. So I will call you that the state C2 is this state, and I have to apply this function. Okay? So the idea is the following. So you see that, in fact, we do nothing for the first qubit. So the first is 0, and so I get 0 here. So this is the same for this. So we have minus 0. For this, we have a 1. So we still have a 1 here. And here we have minus 1, and we have minus 1 here. Okay? But for the second qubit, so here we'll get, in fact, the value y plus f of the value x. Okay? So if we have 0 for x, so you will have 0, which is a y value here. And here you have also f of 0. So this is f of the value here. Okay? For this state, so now we will move to 0, and here, so the y value is a 1, so you have 1, plus f applied to the value x, and since x is 0, you have f to the 0. And so this is the same for this value, so you have a 1 for x. So if you have 1 for x, so the y value is 0, so you have the y value, which is 0, plus f of x, which is f of 1. Okay, so this is the same also for the last term. Okay, so let me just, in fact, try to factorize the output, because it's a little bit long. So I can do this, in fact, using some elegant way. So if I look at more closely at this term, so it's a sum of 2, and if the value f0 is a 0, so I will get, in fact, 0, 0 for the first, and here I will get minus 0, 1, okay, if f0 is 0, and if f of 0 is 1, so I will get 0, 1, which is, in fact, here is minus 0, 1. And here, if f of 0 is 1, so 1 or 1, it will be 0, and I will get minus 0, 0. Okay, so this is the value here. Okay, so I can see that there is some close relationship between these two values, and then I can summarize these two outcomes using only one formula, and I just have to raise minus 1 to the power f of 0. Okay, if f of 0 is 0, so this value will be 1, and I will get the value here. And if f of 0 is 1, so this will be minus 1, and I will get the value here. Okay? So now we have the state psi 3, and so I have to compute the state right after the Hadamard on the first qubit. And so just I rewrite everything here. So the value B here can also be write more compactly. And so this is what I've done here, okay? But it's not complicated to follow the computation. Okay, so now I have the state here, and I just have to apply the Hadamard transform on the first qubit. So if I have 0, 0, I apply Hadamard on this, so 0 will be 0 plus 1. Here I have 0, so it will be 0 plus 1. Here I have 1, it will be 0 minus 1, and here is the same here. If I develop everything, I will get this formula. And so I can rewrite it a little bit more compactly. So in the basis 0, 0, 0, 1, 1, 0, and 1, 1. And so I have to figure out what will be now the coefficient on each basis vector. Okay? So if I have, if the function f is constant, so you can assume that maybe f of 0 is equal to f of 1 is 1 or 0. So you will get, in fact, plus or minus 2. So it will encompass both cases. And if f is constant, so you can see also that this value is 0 and this value is 0 also. Okay, so you can see that if f is constant, in fact, both of these terms will cancel out, and you will only have a qubit state which is described by the first two basis vectors. Okay, that means that if you measure, in fact, the first qubit, and if it is 0, so that means that if it comes from either this one, so 0, 0, or that one, so in fact, you will see that you will get 0. Okay, so if f is a constant, so the first qubit will be 0, automatically. Okay, and either, in the second case, if f is balanced, so you can see that this is the other way around, and this, all this value cancel, and you just obtain the value here, and you can see that these two states begin with a 1. Okay? So I think this is a very simple example that allows you to maybe be more familiar with quantum computation. And yeah, so now just as an exercise, I just will show you what is a circuit, in fact, when n is equal to 2. And in this case, you can see that you can begin with, so the first two qubits is 0, 0, and this is 1 here. And now you have a 3 qubits oracle gate. And at the end, you have to apply the Hadamard transform on the first two qubits, and you have to measure the first two qubits. And this value allows you to answer the question. And in fact, if you do exactly the same computation that I did before, you can see that, in fact, if f is a constant function, so you can see that the final state begins with this state. And in fact, if you get 0, 0 for these two, in fact, you are sure that the function is constant. Okay? And if you get some other value, so either 0, 1, 1, 0, or 1, 1, you can assume that the function is balanced. Okay? So as I told you, you just have to see, and you have the promise that the function is either balanced or constant. Okay? It cannot work if you have as an input any function on 3 qubits, and if it's the case that, for instance, the majority function is not balanced or constant. Okay? So this is a little bit boring to look at all the computation, but I think it's a good exercise to practice quantum computing. Okay. So now let's move on to Shor algorithm. And it's a little bit more complex. But let me before recall you some basic result on some arithmetic on RSA. So I assume that all of you have followed some RSA course. And so I recall you some basic mathematical fact, but they are not very complicated to prove. So the order of some element is the smallest positive integer, such that a raised to the power r is equal to 1 mod n. Okay? That means that if I look at all the power of a, there is no power of a, such that, for instance, a to the k, with k strictly less than r, that is equal to 1. Okay, so I want to have k different from 0. So now, using Lagrange theorem, so you can prove that, in fact, R is a divider of the number of elements in this group here. So the number of elements in this group is phi of n. So phi is, in fact, some unknown value for RSA. And in fact, I think you can know that if you know n and phi of n, you are able, in fact, to recover the factorization very efficiently, because basically you know the product and the sum of the two primes. Okay? But now, if I look at the power of A, so in fact they form some subgroup of Z over NZ star. And this cyclic group, in fact, so Lagrange theorem says that the order of the subgroup divide the order of the group. And so that's the reason why R is a divider of I of n. Okay? So, in fact, you can also prove that R is a divider of the exponent of the group, but I don't know if you know about such a more precise result. But here, you can just assume that it's a divisor of the number of elements. Okay? But we are interested in looking at what is the smallest period for some function. Okay, so the function that we are interested in the functions that map, in fact, the integer k to the a to the k mod n. Okay? So the first assumption that we will do during this talk is that the order of a is an even number. Okay? But it's not a very hard assumption. In fact, it happened with high probability. With probability 1/2 is the case. So from now on, we assume that this is the case. And also from this assumption, we can also rewrite the first equation here. So we can put the 1 on the other side, and we can factor, in fact, these two. Into a to the power r divided by 2 minus 1 times r to the power r divided by 2 plus 1 is equal to 0 mod n. So the second assumption that we do is that, in fact, the value here is not divisible by n, sorry. And this will happen, in fact, with high probability also, so it's not a big deal to assume that we will be in this case also. Okay? But if we assume both assumptions, in fact, we can see that we can get automatically some non-trivial factor of n. So it's just, you can do this, it's not very complicated. And in fact, you can see that n is not an integral domain, and that means that you can have a zero divisor, and it's exactly what happened here. Okay, so in fact, you will get the 2 and the factor 3 automatically if you have such a decomposition. Okay, so let me show you some examples. So for instance, I took n is equal to 15. If I choose a is equal to 2, so first of all, I check if a is co-prime with n. So this is another notation for the GCD. So if a is co-prime with n, so the order of a, so this is 2 to the power 4, so it's 16, and R, so the order of 2 is 4, mod 15. Okay? And you can see that if you compute this GCD, so you will get, in fact, 2 to the power 2 minus 1, so it will be 3, and the GCD of 3 and 15 is 3. Okay? So you can do also the same if I replace here the minus with a plus, and I will get 2 to the 2 plus 1, so it will be 4 plus 1, it will be 5, and the GCD of 5 and 15, it will be 5. Okay? If I begin with 3, so I have automatically found some non-trivial divisor of n, so I can stop here, and so it's very easy to factor n. And if I begin with 11, so you can do the same computation as before, and you can see that you can in fact recover one non-trivial divisor of 15. Okay? So let me go back to our basic fact. So now we have the function f, but it's not, in fact, a bijection. So I will transform this function into an oracle function, and it's exactly the same as before. I just map k0, in fact, to k and a to the power k mod n. Okay? So this will be my function. And so in the previous example, you can show that, in fact, you have some periodic function. And if you do exactly the same computation, so here you have, here I have 2 to the power 0 mod 15, so it will be 1. Here it will be 2 to the power 1 mod 15, it will be 2. 2 to the power 2, 4, 2 to the power 3, it will be 8. And now I have a 2 to the power 4, and 2 to the power 4 is in fact 16, which is equal to 1 mod 15. Okay, if I have a begin with 5, so I have 2 to the power 5 is 32, and 32 is in fact is congruent to 2 mod 15. If I begin with 6, so I have 2 to the power 6 is 64. It will be 4 mod 15. And to the power 7, it will be 1 to 8. And so mod 15, it will be 8. Okay, and you can do everything. And here you see that the function here is periodic. Okay, and the period is 4. And so the goal is, in fact, to recover the period of the integer a. So now what the circuit will be the following. So we will have, in fact, 2 different registers. So the first register will, in fact, store the value k written in a binary decomposition. So here it will be exactly a 1 bit. And at the output, there will be also the same register, because so I initialize with this state, and after the oracle, so the first register will still contain, in fact, the value k. Okay? However, for the second state, I begin with the whole 0 state, and at the end, it will store, in fact, the binary representation of a to the k mod n. And so that's the reason why, since n has a small n qubit, so I have a register here using small n different rows. Okay? So now the initialization of the circuit is very similar to what we did before. So we initialize with a whole 0 register for the first register and the second register. And now we apply, in fact, the Hadamard gate on the first register. And so what is the quantum state here, right before the oracle gate? So right before, in fact, if you apply the Hadamard gate, so this is the notation to apply edge in parallel for the all different rows here. So at the end, you will get this state. So you can do the maths if you want with n equal 1, 2, and it's not complicated to see that at the end, you have all the different representation here, and here you have some normalization factor, but we don't care about it. And the second register will still store the 0 value, okay? And right after the Oracle gate, so we'll get, in fact, here, hold the value k, because the first register is not affected by this gate, and on the other side here, you will get a to the k model. Okay, so this is the value here. Okay, it's clear? And so the goal now is to measure the second register. Okay, and if we measure the second register, in fact, we will have here a state which below from this register. Okay? So this is why it's important to understand partial measurement in Shor's algorithm. Okay? Yeah.
So in the circuit, where are you encoding the bit string of the number?
So
you have a number you want to factor, right?
Yeah.
Where are you encoding it in the circuit?
So the number is encoded here. In fact, the number A and N.
Oh, the Oracle is doing this, right?
So A and N is encoded in the function here.
Yeah, okay, thank you.
Okay, so thank you. So it's a good question. I will go back a little bit later. In fact, I will not show you how to implement this Oracle. However, it's very important to understand how it works, and I will come back in the conclusion. Okay? Now I will make a third assumption, but this assumption can be removed a little bit later. And so you just have to assume that it's true for some slide. And so now, what is, so we assume under assumption 3 hold. That means that the order R is in fact a divisor of 2 to the n. Okay, so for instance, if we begin with, if we try to factor 15, so R is equal to 4, and we see that, in fact, this is a case because 4 is a divisor of 16, for instance. Okay, but now it will allow us to rewrite, in fact, the state more easily, and in fact, to understand what is the effect of the periodic function. Okay, so now let me divide, in fact, the number k by r, and so if I do this Euclidean division, I can always written this k as alpha times r plus beta, and beta is smaller than r, and alpha is anything between 0 and 2 to the n divided by r. Okay, and I can do this for all the different values of k. Okay, and so if I rewrite this state, so here the state is from k equals 0 to 2 to the n minus 1. So I have here all the power of k, and now I will try to compact them according to, in fact, what will be in the second register. Okay, because we have to understand what is the effect of the partial measurement of the second register, and so it's a reason why we try to compact every other qubit or to factorize, in fact, according to this value. Okay, so now I can split this sum between k and this value into 2 different subs, for a sum on beta and another on alpha. And here I just replace the value k by this value. So during my talk, when I wrote underline k, that means that I can also write this using the n-bit binary decomposition of k. Okay, so this is a well-known definition. And so this is also the same here. Okay, so the value k is unaffected. And here I have some effect on the second register. Because if I have a to the k, So a to the k is equal to a to the r to the power alpha times a to the power beta, and a to the r is equal to 1, and so a to the power alpha r is equal to 1, and so at the end I only get a to the power beta. Okay? So it's just I took into account, in fact, the fact that the order of A is R. And so if I measure the second register, in fact, I will get some value beta for the second register, and it will automatically map, in fact, this rule value into only one of this sum. Okay, so here I will get only one of these. Okay, so this is the effect of the partial measurement of on the second register. Okay. So now let me explain you that we are not done, because one thing that we can do, for instance, is that we can measure the first register, and in fact it will give us some value which is alpha 0 times r plus beta 0 for some completely random value of alpha 0 and beta 0. Okay? And so we will get a number, but we don't know alpha 0 and beta. So, no, we know beta 0 because we measure it, but we don't know, in fact, alpha 0. And so we cannot do, so it's not easy, in fact, to recover r from this value. Okay? So one thing we can do, in fact, is try to reduce the whole computation and do exactly the same kind of algorithm. However, we will not be sure at the end that we'll get, in fact, the same value beta for the two different iterations of the algorithm. And so, in this case, it's not very easy to have two different states here with the same beta 0. Okay? In the same way, we cannot also have a first measurement and try to clone the state right before the measurement on the first register, because we cannot clone state, as Giulio mentioned before. Okay? So this means that we need to do something different. Okay, so this is exactly where we will need, in fact, the discrete Fourier transform to solve this problem. So let me just present you some working example. So I begin with 0, 0. Right after the Hadamard transform, I have the sum of the rule state for the first register, and for the second register, I have 0. Now I apply the oracle that allows you here to have a to the power 0 mod n, a to the power 1 mod n, and a to the power 15 mod n. If I rewrite this state here, you can see that, in fact, since I assume that R is a divider of 2 to the n, exactly I have this, for each row, I have the same number here. And here, so you can see only this value. Okay, so this is a working example that I begin with for the function at the beginning. And then assume that we measure, in fact, for the second register, the value 4 here. So we get beta 0 is 4. And so the first register is, in fact, the sum of the value here. Okay, so we get the sum of this quantum state. And so you can see that, so we have some value alpha 0. And then we only have, so all the value here are well separated by the order R. However, we need to, in fact, recover this value. Okay, but we cannot have this value and that one because we cannot clone state, and we cannot also reduce the computation and have this value and have this one with another different beta. Okay, so we know that this state is very interesting. However, we need, in fact, to recover the 4. Okay. And what exactly the inverse Fourier transform will allow us, in fact, here R is in some way in the numerator of some function, and our aim is to transform the R, which is in the numerator, into the denominator. Okay? And it is what we will see using the Fourier transform. Okay? Have you any questions so far? Yeah?
Sorry? Just quickly recall the inputs and outputs of the oracle.
Yeah, so
was defined. Sorry, was...
yeah. So maybe it's, oh, sorry. Oh. Sorry. So the input of the oracle here, it will be, so the input is this state.
Yeah, okay, so the second half is the zero register. Okay, yeah, thank you.
And here, yeah, and here you have, I remove the mod 15 for every,
yeah.
Okay.
That's enough for me, thank you.
Okay, thank you. Yeah.
How clear is it that A to the K and A to the K plus R as a quantum state are the same? It seems to me that you were using that in the previous slide, or you were kind of factoring theta out.
So can you repeat, please? Maybe so which side?
This one.
So it's fine, this.
Right there. Are you using that A to the K and A to the K plus R as a quantum state are the same somehow?
No, I think, so the state is just, so the first register is K, and the second one is A to the K mod N. And in fact, here I just rewrite the state like this, but it's exactly the same state. It's just easier to see, to understand how works the partial measurement when I written the state that way. But in the sum, the sum here is exactly the same. You don't?
I see if state A to the K, and let's say A to the K plus R are the same, but as a, you know, not just as a thin mod N, but as a thin...
Yeah, I assume that the order of A is R.
Yeah, sure.
Yeah.
Okay, okay.
So I don't understand why...
Yeah, I just think I have to think about it a bit more.
Yeah, okay, so that's why I try to put this example to see exactly what is going on here. So yeah, we need to do something different, and so the idea is to use the discrete Fourier transform. So let me just recall some basic fact about complex number. So if you sum all of these values, if z is 1, so you just add 1 n time, so you will get n, so it's easy. And if z is not 1, so you see that here you have some geometric sequence, and so it's not difficult to see that the sum of all of these values is that 1. So I think maybe you know the trick. So you call this value capital S, you multiply this value by z, and so if you subtract the two different sums, so you will get that all the middle term will cancel out, and so at the end you will get only 1, and the value here that will be z to the n. And so if I do this, I can also put factor by 1 minus factor by s, and so at the end you will get this value. Okay? So what is important is that, so this lemma is important, it's called the crucial lemma. So it means that if I divide this value by n, in fact I will get 1 for the first position. So the first position is when, in fact, j over n is in fact an integer, because in this case, here I will have only 1, so I will get, in fact, this value, and I divide it by n here, so it will be 1. And on the second case here, so you can see that this value is in fact an nth root of unity, and so this value is in fact equal to 1. And so at the numerator, you compute 1 minus 1, it will be 0. And so that's the reason why here you got 0. Okay, so either you get 0 or 1, and it's a very useful thing, and maybe some of you know exponential sum, but you can do a lot of things using such function. Okay, but the discrete Fourier transform is defined like this, in fact. So you can see that for some qubit k, in fact, you do some linear combination, and here you have some normalization factor, and here you have some complex amplitude. And so the only difference between the inverse Fourier transform is that here you have a minus, and here you have a plus. Okay? So there are well-known transformations, as Giulio presented this morning, and there are two basic important facts. So one of them is that this is a linear operation. So if psi is a superposition of some state, so you can apply, in fact, f on each different state here. And so other part is that it is a unitary, and so you can describe it using a quantum circuit. Okay, so the fact that this is unitary is not very complicated. It's just you need to use, maybe if you want, I can add it in my slide. So you just want to see that some characterization of unitary matrix is that they transform orthonormal basis into another orthonormal basis. And so the only thing that you have to do is that the transformation of the discrete Fourier transform will transform, in fact, an orthonormal basis into another one. And that means that the operation is unitary. Okay, so it's just math, and it's really not really interesting. Okay. So now the only difference is that here I had the Fourier inverse transform is that basically is kind of the same thing that we do at the end of the Deutsch and Jozsa algorithm. We apply, in fact, the Hadamard transform. Here, in fact, we apply the inverse Fourier transform. Okay? And now, if we apply this, in fact, and we measure the first register, we will get this value. And it is exactly as I explained you before. It will, so the function here allows us to switch, so the R was in fact in the numerator, and then I have been able, in fact, to transform the R in the numerator into the denominator of this fraction. Okay? And usually from this state is very easy to recover R, and if we are not able, in fact, to recover R precisely, we will get, in fact, a factor of R, and we can redo, in fact, the computation after. Okay? So once you get, in fact, a factor of R, it's not complicated to know R. Yeah?
Just what's L in the second last bullet?
L will be some integer. So I will describe them a little bit later, but here I just show you that you have a fraction, and so you, on this fraction, so it's not anymore, so the first register will not anymore be an integer, it will be a fraction, and from this fraction, so this is the numerator, and here's the denominator of the fraction. Okay. Okay. So after the partial measurement, so here we fix the value beta, and so now we have to apply, in fact, the inverse Fourier transform. Okay, so this is a sum of different value, and f minus 1, so the inverse of f is also linear. I can apply this to all state elements, and so it will allows me to have now another sum. So I have a sum of the whole value here. And here I have some weird value. And so I can switch to some because there are a finite number of elements. And now I can apply my crucial lemma that says that this value here will be 0 or 1 according to some value here. Okay, so this will allow me to simplify the sum here because sum of this value will be 0. And I only get 1 when, in fact, j divided by 2 to the n divided by r is an integer. And so in this sum, I can only have some value j that are very specific, and so that this value are some integer. And so this is this value that is an integer that I call L. Okay, so L is in fact just, I simplify the value because it's a little bit complicated. And so I just make a change of variable and I will call this value L. And so in all this value, I can replace this with L and R over R. Okay, so this is just a rewriting of j divided by 2n with L divided by R, and I do only this value for the different value L, and in fact I can show that I have only R such value. Okay? So this is maybe a bit squarey at first glance, but it's not very complicated to understand how it works. Okay? So now that I did it, so this is so the state of the first register, and if I measure this, I will get one of this value. Okay, and one of this value is one of a fractional number. Okay. Okay, so I will get this for one of them. I don't know exactly the value L that I have. Okay, but I have maybe L is equal to 0, 1, or R minus 1. And so from this value that I recover, I can recover the value from one of these states. Okay? So exactly, you can see that the effect of the discrete transform, Fourier transform is in fact to transform the value R that you have here in the some kind the numerator of some fraction divided by 1, and here you have R on the denominator. Okay, so this is exactly the purpose of this transformation. Okay, and once you have recovered this value, so in fact it's not very complicated to recover the value R. Okay, so I recall you, so you know M. You know also small n here, and in fact you are looking for the value L and R. Okay? And so the first thing that you can do is that you divide m by 2 to the n, and so you will get some fractional value. And so now so the goal is to recover the value R. Okay? So maybe in some rare cases, so the value that you recover here is in fact an integer, and you have no information on R, and so you are, so you just have to reduce the whole circuit with some other value. Okay? If on the other hand, so L and R are co-prime, so this fraction is irreducible, and then in fact it's not very complicated to recover R, because you just have to read the denominator of the fraction. And if L and R are not co-prime, so in fact you can, here the fraction you can make into irreducible factor, and this will be this value, and you will see that in fact R prime is a divisor of R, and so you get in fact a factor of the order. Okay, and once you have a fraction of the order, in fact, you reduce the computation, but now using a to the power R prime, which is the factor that you get. And now the period will be R divided by R prime. Okay? So now it's easy. However, so do you have any questions so far? So I have only one call to the function f, and to the circuit that represents the oracle f, and one call to the discrete Fourier transform. And here I only have to reduce, some computation, but it will not be a large constant. With high probability, I will get some order or some factor of the order. This is okay. What? No, it's.
But we have to redo the call, right? We have to call the oracle once again if we got the L prime.
Yeah, so we have to reduce the computation because also I assume that R is even. And also because of, so the second assumption that I made, I don't remember, but it will happen with probability 1/2 also. So at least I have to reduce the computation 4 times, and if some bad cases happen, I also have to reduce this. But it will just be some constant number of factors. Okay.
So if you go back one slide, so when we just look at the cases where we have to redo the computation, so I think I see in the final case that we kind of get closer and closer. If you take the factorization of this R, I can see that this probably doesn't take too long. But can you say something about the case where X is an integer? The second, like, how likely is this roughly, or that we have to, so the second bullet point where we have to...
Yeah, we can bound, in fact, the number of times that we get an integer. It's not
is it like uniform or like, can you, I don't know, I have no intuition on how likely this is, or
maybe sometime is that, for instance, it happens that L can be 0. And so in this case, you get 0, and you get, in fact, no information in this case. Okay? And if R is also a divisor of this fraction, so it can be an integer. Okay, but since L is basically, if you see this, so this will give you the probability to happen with this state. And so there is no reason why, in fact, R will be a divisor of this.
So it depends on the value of L we get, but there's not too many. I think I see now where this is a problem. Okay, thank you.
So it's a randomized algorithm, I agree. Okay. Okay, but now what I want to show you is that, so I assume that R is a divisor of 2 to the n, and now I would like to remove this assumption, and I would like to show you that we can do this, and it's not much complicated. However, the idea is quite nice. It's used, in fact, what is called a continued fraction. So basically, a continued fraction is, in fact, just lattice reduction using 2 by 2 basis. So it's easy, as Daniela mentioned, so it can be done in polynomial time. But however, there is another way to describe this kind of algorithm, but is very similar to what we do during the lattice reduction. Okay, so assume that you have some fraction. You can always, or some you can always, you can always describing as follow. So here you have A0 plus, so all the AI here will be integer, and so I will represent this whole fraction using this kind of notation. Okay, so this is just to make this notation a little bit shorter. And so, for instance, if you have 5, 2, 1, 4, so A0 is 5 plus 1 over 2 plus 1 over 1 plus 1 over 4, and it will be this value. And if you begin with only the first value here, you get 5. And now you put the second value, you get something closer than this value. and so on and so forth. And at the end, you will see that if you get the 3 different values here, so you get something that is very close to the whole fraction here. Okay, but it's a very useful tool, in fact, to well approximate some fraction or some irrational number. Okay, so let me explain you how it works for some irrational numbers. So you have the value pi here. So you can always approximate it using so the only first 2 digits. So it will give you 4 divided by 100. And so the denominator here, you can see, is fairly large. Okay, but I can, in fact, approximate this value using much shorter, in fact, value here. So the idea now is that I have this value. I can split it in 3 plus 14 over 100. And so I invert, in fact, this value. And so here I get something where the numerator is larger than the denominator. In fact, if I do the Euclidean division between 100 and 14, I will get, the quotient will be 7, and the remainder will be 2. Okay, so I can rewrite this using this sum of 2 fractions. And now here I have a 2. Divided by 14, and so I can in fact simplify this value by dividing both terms by 2, and I will get this value. Okay, so this value is in fact represent in fact this value in exactly the same way. So this, using only 3 integers, I represent some approximation of pi. But I can do in fact better. If I look at only on the first 2 digit here, I can in fact recover maybe one of the most well-known approximation of pi, which is 22 divided by 7. Okay, so you see that you get some, so the first 2 digits are correct. However, if I do a much more precise operation now, if I take only 5 different, the 4 first integer, I can do something which is fairly comparable with this value here, okay, using a continued fraction, because here you have 300 something, and here you have 100 something. But nowadays, using a continued fraction, so you can see that you have in fact a 6 correct digit instead of here you only have 2 correct digits. Okay, so continued fraction allows you to in fact have a very good approximation of irrational number and rational number. So, yeah. So assume now that, so this is some value. I want to factor 21. So it's not a big deal, but let's do what we can do. So now, n can be in fact 512. And then assume that at the end, you get, for the first register, you get this value. Okay, so from this value, you can divide it using 2 to the n, and so you get this fraction. And now the question is, what is a good approximation of this value? Okay, so if you just divide everything and you just look at what is the closest small integer representation of this value, maybe you can see that a good approximation will be 1/5, 4/5, and you can maybe assume that the order is 5. Okay? But in fact, it's not really the case. So one good thing you can do, in fact, is you try to write the continued fraction from this fraction, and you will get this. And so you get, in fact, into what is called partial conversion. So you just take, in fact, the 2 first digits, you have some fraction, and now you use only the 3 first digits, you get another fraction here, and now you take only the 4 first digits, and you get this fraction here. And now you see that the denominator goes from 6 to this value. And this value, in fact, is larger than 21, the value that you want to factor, and that means that maybe 6 is a correct factor of R. Okay, so this is exactly what we will do next. Okay, we do exactly the same as before. However, we got some fraction at the end, and we compute the continued fraction of this value, and then we take, in fact, partial conversion up to the case where the denominator here is larger than n. Because we are looking for some order, and we know that the order is smaller than the value that you are factoring. Okay? Yeah.
We only need this if the numerator and denominator are not relatively prime. Or, right? I'm just asking, like, in which case we need to use the strategy.
You can do this strategy every time, in fact. It works every time. So, but it's simpler if it is just simpler if in the case when I have the third assumption, but if I have not the third assumption, this is working also.
Okay. Okay.
Okay. Okay. So let me describe what we can do with arbitrary order. Okay, with arbitrary order, I mean that the order R is maybe not a divisor of 2 to the n. Okay, and now I have another idea is that I also assume that 2 to the n is larger than n squared. So this is, in fact, in order to apply some one-not theorem, and so it's I need to have the assumption. Okay. So I try to factor 21. So I begin with also with the same kind of thing. Here I see that R is equal to 6. So because it's 2 to the 6 is 64, and 64 mod n, in fact, is equal to 1. And also we can see that R is not a divisor of this, and so we can see that we can recover this value. So let me just explain the difference between the case when I assume that R is a divisor of 2 to the n and that case, is that now when I arrange all of these values, for instance here, the first two rows have 86 different values, and the other one have only 85. Okay, so this is not rectangular because all the rows have not exactly the same length. Okay? So assume that we measure the second register, so the second register, and the second register will give us the value 2. That means that the first register, in fact, contains all of these values. Okay? So now I apply the inverse Fourier transform on this state, and it will give us this value. I can do a little bit more value. And so the main difference is that the values that you have here nowadays are no more 0 or 1. Okay, so I cannot apply, in fact, what I did before using the crucial lemma. Okay, this is something that is different from 0 and 1. However, what that is very important is that, so as I said before, so the value is not 0 or 1 exactly. Okay, so the state is not as simple as before, but we can see that it's not very different, in fact. You can see that if I plot all of these values, you can see some peaks exactly close to the values that we are looking for. Okay, so if you are this value, so you can see that all of the different values for the register J, you have some value, but some of them have a very small probability, and some of them have larger. For instance, you can get, in fact, this value, this will be this peak, and from this value, so you can, in fact, divide it by 512, and so if you compute the continued fraction of this value divided by 512, you will get, in fact, the value R that we are looking for. And this is exactly the value 6 that you are looking for. Okay? So this is just with a working example, but I think that it's maybe easier to understand what happened. Okay. So what is the lemma that we use is that it's written in Hardy and Wright book on number theory. Is that it means that if you have some rational value, some fraction here, and you have some value x, and you have a very good approximation of this value, in fact, you can recover the fraction here very easily just by looking at all the continued fractions that you have. So by looking only on the partial convergent of this continued fraction. Okay, so this is exactly that we did. And why we can apply this theorem is not difficult, is that if we have the closest integer close to this value, so we have some value m that is not too far by 1/2 from this value. And now if I divide it by 2 to the n, so I will get this value. And now I will call you that I assume that the value 2 to the n is larger than n squared, and n is larger than r. And so I can do the math and show that we are in the same situation and we can apply this value. And so just by looking at all the partial convergent of this fraction, in fact, by looking at all of them, we can in fact recover for one of them the value here. And you only have, in fact, a polynomial number of such convergent. And in fact, the best you can do, in fact, is you just look at all the convergent. So the denominator is going larger and larger. And once you are greater than n, so you stop and you just use the value before, and usually it will be the value r. Okay, but otherwise you can also try all the different values that you get before, and one of them will be good. Okay? Questions so far? No? So since I do not have much time to look at the discrete Fourier transform, let me just maybe explain you how you can look at the slide maybe more carefully. So the idea here is to rewrite, in fact, the definition here using some factorization. Okay, so this is the first step. And so I show you how it works for n equal to 1. And then, so the idea of showing that these two definitions are equivalent is that for each different value k, so you can prove that the value that you get here, right before the register here, is exactly the same for each different value of j. Okay, so this is just by written the binary decomposition. And so this is not very complicated. Here you have a product, and in this product, either you take only, for instance, the 0 coefficient. So if on each product you use this value, so you will get by 0, 0, 0 n time, and so this will correspond to this register, and from this register you will get only 1 time 1 time 1 time 1, and so you will get 1. So this is exactly the values that you get here. Otherwise, if you get some value from 0 and sometime for 1, so you will have to switch sometime, and basically you will recover, in fact, the decomposition of the value j that you begin with here. Okay, so you can, in fact, summarize everything. So it's not, so the proof is not very complicated. It's just you prove that for the two different decomposition, it will give you exactly the same value. Okay. So there is also another way to write this, and this is just using some fraction decomposition. And now I put two comma here to write, in fact, some fractional number. So if I put two different commas, so this means that G1 over 2 plus G2 over 2 to the 2, and so on and so forth, so it will represent this value. Okay, so this is just a working example. If I have this value, so I can return this using binary, and it will represent 1 over 2 plus 0 over 4 plus 1 over 8. Okay, and so the main idea of this corollary is that in the factorization that I showed you before, in fact, you can rewrite all of these values using fractional number. Because in fact, if you have some value not in the fraction, in fact, the whole value that you will get here, you will just allow you to multiply by 1. And so it's meaningless, and so you can completely avoid it. And so on each different factor, term in the product, so you can in fact just remember, so it's just 0 dot dot k0, so this means that it's k0 divided by 2, so this value is k0 divided by 2 plus k1 divided by 4, and so on and so forth. Okay, so this is just an easiest way to in fact represent the Fourier transform. And so the proof is very easy. Just divide this by 2 to the L. You show that this is an integer value, so I can write it using p. And when I develop this value, I get 2 to the I times pi times p. And since p is an integer, this value will be 1. And so at the end, only what is matter is this value. Okay, so this is what this value is important. Okay, so I show you how it works for some value L. And then let me just show you that it works. So in fact, you can implement this. So you get in fact some fraction, some gate that do some rotation on the second qubit. So here is the first value of R. And so now, these two qubit gate are also a control gate. And so according to the value on the first qubit, if it is 0, you do nothing, you do not apply R. If the first qubit is 1, you apply R on the second register. Okay, and in fact, you can show that you can implement every term here. So for instance, if you look at only for the first line, so you just apply the Hadamard transform here, and the Hadamard transform is exactly this. Okay, so the Hadamard transform is a plus if k is equal to 0, and it's a minus if k is equal to 1. You can rewrite this using this value, using k0, because if you have 0 dot dot 1, so it will get minus 1. And so this will be a minus here if it is 1, and if it is 0, all these values cancel, and it will be ket 0 plus ket 1. Okay, and you can do exactly the same for this value. This is exactly what I did here. It's very easy to follow. And more generally, you can see that, so we can show that these two values are correct, and you can see also that these values are correct. Okay, so this is this seems to be very complicated, but it's very an easy quantum circuit. Okay, so now let me conclude. So there is one generalization of Shor algorithm, which is called for some problem, which is called the hidden subgroup problem. So the problem is let G a group and H a subgroup. And so let's assume that you have a function that is constant on each coset of H. And the goal, in fact, is to find H. Okay, so this is very convenient, in fact, because you can more or less rephrase everything that we did with Shor algorithm in this case. But so the only thing that you see is that now you can also work with a group G that you don't know, because you don't know phi of n, and so the algorithm is still working. Okay? So there is another algorithm which is called Simon algorithm, which works on this group, and it works for this kind of subgroup. And so this is exactly the same kind of algorithm, and it works also. And more generally, Kitaev generalized this for every abelian groups. And you can do this using some character to define the group. And for non-abelian groups, so this is a very interesting case because you have some algorithm which is called, which can be described by Kuperberg. And so also Regev show some very interesting relation between breaking some lattice problem and solving the HSP problem for some non-abelian group. And a lot of results are known now on this kind of result. Okay, so if you want to break, in fact, lattice problem, so this can be, in fact, an interesting case to look at what kind of special non-abelian group you can solve. Okay, so Shor algorithm is quite, so there was a lot of recent result on the factorization. So Shor backs to 1994. So this is a very nice algorithm. But last year, Oded Regev described some different algorithms that allows us to, in fact, reduce the number of gates by a square root of n. However, he increased the number of qubits. More recently, Raghavan and Vaikuthanathan show that they can do the best of both worlds. So they can work with n to log n qubits and with the same number of gates as Regev. And more recently, we show that we can also work with less than n qubits. So this is something that is very surprising for me, because I thought that for breaking, for instance, RSA 2048, you need that number of qubits. However, we show that we can do this with less than 2,000 qubits. We can also adapt it to the discrete log and show that so you can really go to O of n qubit. And so this is, you want to, in fact, give you some concrete parameter, and there is some constant that is quite large. So this is why this number is not very small. But for the DL case, they can be, in fact, smaller. Okay. So the conclusion is that so all the algorithms that I described, in fact, work for logical qubits, and how far are we to factor? So in fact, Gidney and Ekera some years ago did some exact computation, and they found that in fact they need 8 hours using 20 million of noisy qubits to factor 2,000 bit RSA modulus. So this is quite large. So this is because you need a lot of physical noisy qubit to implement logical qubits. Okay, and so I just want to give you 2 different reading if you are interested in working in quantum computation. So this is Nielsen and Cheung book, so it's very important, and you have all you want to know. And so the second one is by Andrew Childs, which is his lecture note. We give you more about the generalization for the HSP problems that I've described quite quickly. Thank you very much.